And working with higher dimensional functions, one of the things that we might want to do is compute a partial derivative. And the beautiful thing about this is it works exactly the same way as with two variables. Doesn't matter if we have 2, 3, 4, or 10 variables, the partial derivative calculations work the same way. The only difference is we have more derivatives that we could take because we need more information to perfectly describe the rate of change of our function if there's more variables. But the key thing is we hold all the other variables fixed. So in this example here, we have a function of 3 variables, x, y, and z. We are asked to compute the derivative, the partial derivative of f with respect to z. If we're doing that, we look at our variable list and we treat x and y as if they were constants. And that makes sense. That's the idea we have in this derivative anyway. The idea is we're going to have a small increase in z, and we want to know the change in f. Well, if we're only increasing z, then y and x are not changing, so we leave them or we treat them as constants. All right, let's do the actual calculation here. We can write that derivative either with the partial derivative notation, the Leibniz notation here, or with the subscript z again. Either way is fine. But notice we have to treat z as an input for this function now, not as our usual output. But we just go ahead and scan for z's. All right, there's a z there. So we have an x multiplier. We have an e to the something. The derivative of e to the anything is e to the same thing. And then we take the z partial derivative of the exponent. Well, that's going to give us a constant times z's derivative. It's just the constant or just y here. Next term, we're done that one, is z squared times all this stuff here, but x and y are constants, so this entire term is a constant. We simply get the derivative of z squared times the constant, and we are done. So there's no fundamental process change in taking derivatives of other variables. We just treat everything, any other variable that's not in the derivative, as if it were constant. We'll do some more practice to reinforce this. If we're taking the y partial derivative of this g function here, we scan for y's, and we notice that this function here has 2x in the bottom. It might feel like a quotient rule is appropriate, but I would rewrite this to start with as simply 1 over 2x times x squared y plus 3, oh, there's another y in here, plus 3y e to the zy. And this, if we're taking the y derivative, is a constant multiplier. So our partial derivative is simply 1 over 2x times the derivative of the rest of the term. And what does that look like? Well, the first term is easy. We have x squared, treat it like a constant if we're taking the y derivative, times the derivative of y, which is just 1. We don't write that. This next term, though, has a y in 2 positions, and so here we're going to need the product rule. This requires the product rule. Fair enough, we can do that. We'll have, let's say, treat the 3y as the first term. We'll have 3 times 1 times e to the zy, no change, plus the first term, 3y, times the derivative of the second term. And the derivative of an exponential is the same exponential again, times, as we saw in the last example, the derivative of the exponent. The derivative of the exponent with respect to y this time gives us constant times y. The derivative is just a constant. And we might tidy this up a little bit. But again, unless you know what you're doing next, there's no sense in going too far down that road. But having 3 times 1 seems a little obscure. So 3 e to the zy plus 3yz, we would probably group those at least out front. And there we are. That's the y partial derivative of g. One more for reference. If we do the partial derivative of h with respect to x and evaluate it at a point, we'll do the same thing we've done before. We'll take the derivative with respect to x, and notice here we have 2 terms that are separated by addition, so we can take the derivative of the first term, The derivative of sine, anything with x, is going to be cos of the same thing. Then we take the derivative of the inside with respect to x. That will just give us a y, the constant multiplier. Then we look at the next term, just an x, perfect. The z cubed is a constant multiplier, we keep that, and the derivative of x is just 1. Last but not least, we include the point we were given now. So this is the general formula for slopes of this function, or rates of change of this function in the positive x direction. And now we specify a point. We simply sub in the values that we were given for x, y, and z. So we have cos of x times y, well, x is 0, so it'll be 0, times y, which is 2, plus z cubed, that's 3 cubed. Cos of 0 is 1, so we end up with 2 plus 27, and that gives us 29. So what would we say about that? Well, that tells us the rate of change of h, if we take a step in positive x, is for each step in x that we take, this function h will go up by a factor of 29, assuming the step is reasonably small. So that's the process for taking partial derivatives with more than 2 variables. And again, there's that nice pattern that it doesn't matter how many more variables past 1 we use, it's always the same approach throughout. Treat all the other variables that are not in your derivative as if they were constants.